So thank you very much for inviting me to give this talk. I'm not a physiologist, not clinician, so I'm not going to deal with the disease. I'm a mathematician, so the question is why mathematician is here, trying to discuss some kind of things he do over 25 years in neuroimaging. So the question is what neuroimaging means. I have no question. I have no answer for that. And I'm going to give just a modest view of the mathematician about imaging and neurovascular coupling in human. People working in my group who are physiologists do a lot of things and propose a kind of well-now established model linking between activity of neuron, extracellular space, astrocyte, and hemodynamics. And it's, for the mathematician who I am, it's really very complex. I'm not sure that we can deal, even if we have some idea about the physiology. For the physiology, maybe this model is very simple. But for the mathematician, this model is very huge, complex model. So the question is, there are a gap between what the physiologist thinks and what a mathematician can help to do, with kind of model he can propose. So we try to simplify this model like this. This is the point of view of the mathematician. They are very far about what physiology is. So if we suppose that all the compartment of the neuronal and astrocyte compartment can be linked as some kind of stimulus. So can I do something with this kind of very simple model? And this is what all the community of neuroimaging do. They just suppose that the bold signal, for instance, is a convolution, is a function of the stimulus, which are supposed to be a neuronal response function and the hemodynamic response function. So this is very, very simple model, and it helps to do a lot of things. Of course, probably not very true, but it helps to do things. So the model, we see that the hemodynamics is not well modeled. So the idea of my colleague Buxton and others try to make a biophysical model to have a kind of variation of the hemodynamics response, because they see that, depending where we are in the brain, the hemodynamics change a little bit. So they include a biophysical model which help to model this. And this biophysical model include variation of the cerebral blood flow, cerebral blood volume, and also the deoxyhemoglobin, as you know, that this is a very clue parameters to interpret the bold signal. Why this model is interesting? So this model is interesting because the model underlines some physical or physiological parameters, like I come back to this one. So, like a group parameters, these parameters help to link quantify the hemodynamics. It's a kind of a morphology of the the capillaries. So if you are interested by the morphology of the capillaries, these parameters help to quantify this. This is not a direct link, but it is mainly linked to, you know. And if you do that, and you do the both bold signal and ISL, arterial spill labeling, and you do those signals to estimate only one parameter. This one, you can, for instance, estimate, you can see that these parameters is, the group parameters is linked to the age. We do some experiments and we see that the neurovascular parameters in a rat model in healthy aging can correlate well to the age. So the bold signal itself does not correlate. And the group parameters correlate. So it means that there are some kind of underlying parameters which the mathematician help to emerge and do some kind of classification or correlation. I'm not at the stage of what physiology is. I'm trying to capture some kind of parameters to help classification, maybe in patients in the future. So if we go ahead to the neuronal activity, a lot of group work on it. And probably this famous paper of Logothetis and his group showing that the local field potential is related to the bold signal in the visual cortex. And this is the first evidence that there are a kind of link. I don't say a linear link, a kind of link between the local field potential and the bold signal. And now, if we do that, so it had the idea behind this, or how my group use it, is to model the local field potential using EEG, for instance, and the bold signal using fMRI. And then we can merge, but how we merge? So we can try to build a model based on Logothetis work. So how we can do that? There are a few models which are now more complicated for the first one I show you, because this model linked the power spectrum of the EEG signal and hemodynamics to get bold. It's not just the stimulus as an input in the brain. So there are several models showing that this link is reasonable somehow. Okay, so now if we want to have an idea, this is the point of view of the mathematician. So the point of view of the mathematician to link between EEG and fMRI, knowing what Logothetis and other groups do, is to extract and conceptualize a model. And this model say that the envelope of the Hilbert transform of the EEG signal is related to the bold signal. This is a concept. And this is what we do. And this is a very general conceptual relationship between EEG and fMRI. At this stage, I'm far from the physiology, too. Okay, so which perspective? And the idea is, okay, can we try to go ahead to the physiology to do something? So I apologize for this moving to the physiology. And I'm going to give some just idea, mathematician idea. So the first thing we can show is that the Schirmer's group show that if you turn the response of the astrocyte and their influence in the hemodynamic signal, you get something like this. It means that they segregate what we called the hemodynamic response function on a hemodynamic neuronal response function and hemodynamic astrocyte response function. This is really very interesting because what all people do is one hemodynamic response, which is the average, which is the average of the two hemodynamic response. So it means that what we get on the Bolt signal is a combination of what astrocyte, the signal astrocyte, and the activity of the neuronal compartment. This is a combination. So if there are a mismatch between these two combinations, so what we see in the Bolt, I'm afraid, because we can't interpret the result, even if we are now able to extract these two parts of signal from the Bolt. And the idea is they are mainly linked, but sometimes, for instance, in the disease, there are a mismatch between the astrocyte compartment and the neuronal compartment. So at this stage, you can do some kind of signal processing to extract a part of what we call neuronal part in the Bolt signal and what we call astrocyte part in the Bolt signal. Okay. So if we come back to this model, and the point of view of the mathematician is not the physiologist, because the physiologist is really interested by all the parameters we get here, not the mathematician. Why? Because the mathematician is interested by the way which variable in this model help to get the main effect of the Bolt signal, of the EEG signal, or whatever. So this is another point of view. For instance, if the lactate explain only 2% of the Bolt signal, for instance, so I consider that this is less than 5%, and I move it on. Okay? This is another point of view to simplify the model and to make this model qualitatively usable. No. So I come back to work of people who are here and look at the, if we try to look which activity influence the cerebral blood flow, and we go to the literature, and we see that the CBF is correlated to the sum of synaptic activity and not post-synaptic activity. And the local neuronal and integrative process can drive the CBF increase irrespective to whether they generate action potential. And then the close correlation between hemodynamic response and neuronal synchronization and the power of LFP oscillation is seen in the gamma range. So if you put all those physiological hypotheses or experimental work together, so you can see that we can hypothesize that variation of the postsynaptic potential activity, the PSPs, influence the variation of the CBF. This is interesting. So it means from the experimental point of view, we can do a link. Okay, second point. So there are some evidence which indicate that the hemodynamic response to neuronal activity is not initiated by signal rising for energy deficit of tissue. This is now well known.
1 minute.
Okay, 1 minute? Oh, I'm sorry. So I go ahead to the conclusion. So, so PSPs, the astrocyte signal and vasoactive mediator mediate the Bolt signal. Again, we can consider regarding the literature that both glutamate and GABA modulate the bold signal in proportion less than 5%. This is only my point of view, okay? And the last one is, so glutamate and GABA are indirect vasoactive mediators. This is also well known. And general conclusion of this work is, look at this. So variation of CBF is related to postsynaptic potential. This is a direct relationship. To glutamate and GABA, this is an indirect relationship. And we can see also that the CBF is related to glutamate and GABA and extracellular and astrocyte compartment. So now we can try to build a model based on the literature. So this model is composed by the main cell, which have to understood what EEG and MEG means, for instance, or LFP, the interneuron, which are mainly related to this compartment, astrocyte compartment, extracellular space, and vascular compartment. So now we can put some kind of equations linking the main part of this model, and it gives something which is more simple than what we showed to you first, but this is the point of view of the mathematician saying that the signal which get with this model represent 95% of variation in EEG, in MEG, in fMRI, and so on. This is a more simple model, and we apply it, and this is my last word. We can generate the LFP, we can generate the extracellular glutamate, GABA, both of them. This is just the sum of two. And we can also look at the hemodynamic response. We can have the variation of the cerebral blood flow by the neuronal compartment and by the astrocyte compartment. And we can also get the bold signal, which is a combination of two. So I just want to thank all the people who are working in this topic in my group. So thank you very much.
Very nice.